Welcome to the April 2nd edition of Kitchen Table Chemistry. Our objective today is to be able to describe what a rate law is. Now, I've already asked you to watch a video on YouTube, so I'm going to try and keep this short and sweet. A rate law will look like this, where we have K. K is a reaction constant. Square brackets for A, which will be the concentration of A. Usually we've used molarity, but it's going to become a lot easier just to put it into a square bracket like that. To the power of M. M is the rate order of A's concentration, and that is what we'll be looking for a lot. What is the order in which the concentration of A is used up in the reaction? B would be a second reactant and would be treated separately from A, and it would have its own rate order, which is done the letter N up there. If we multiply K, the rate constant, times the concentration of A, times its rate order, and then times the concentration of B times its rate order, we will get the rate of the reaction. The rate of the reaction will usually be expressed in the units of molarity per second or perhaps molarity per minute, depends on the speed of the reaction. In the video, the gentleman, Mr. Anderson, demonstrated and discussed to you what is a zero order, first order, and second order reaction, and how in a zero order reaction, the concentration does not affect the rate. In a first order reaction, it is a direct relationship, and in a second order reaction, it's an exponential relationship. We'll end up with graphs like this if we did concentration and rate. Data that we would develop in lab would normally be like this, where we would have concentration and time. So if we monitored the concentration of A, say through something like a spectrophotometer, over time, we would see the concentration of A decrease, and we will create a graph like this. If we then took the natural log of concentration of A over time, we would see a linear relationship develop, and that's how we would determine that whatever A is, it would be a first order reactant, and that would be data that we would want to have. Rate laws are experimentally determined. You can't really just do them on paper. You have to find them through experimentation. And that, by the way, is usually a great part of the fun of the kinetics unit, is doing these experiments. You develop data like this, where you can create a nice rate law graph at the end, where you've got your rates that you have been able to create and your concentrations on the x-axis. This is the linear relationships as they stand. In a zero order, what you'll tend to get is a decrease over time of concentration, just because it's being used up. In first order, it is a linear relationship if you take the natural log of E over time. And then second order is the inverse of the concentration. 1 over concentration over time will give a linear relationship. So it's determining these linear relationships that we'll spend time doing. Tomorrow, we'll start looking at data like this, where we have multiple experiments, and we will try to find from them what the rate orders are. And this is where we'll pick up on Friday. Again, I hope you're well. I hope things aren't too stuffy inside. You've been quarantined now for a matter of time, and you're not getting cabin fever or too bored. If you're still going to work because you are an essential employee, I hope you are safe and people are treating you well at your place of employment. And again, always please let me know if you've got any suggestions for improvements, criticism, or you simply can't access or find things, let me know. Take care. Signing off for right now. Bye-bye.